So this is definitely an interesting one regarding relating rates, and it's because it has three parts, and all three parts are in fact dependent on the previous part. And you'll actually understand what I mean as we sort of progress. So we have a 17 feet ladder, 17-foot ladder, and it's leaning against a building. And the foot of the ladder is 8 feet from the base of the building, and it's sliding away from the building at 3 feet per second. So the rest of the questions that sort of follow after this particular piece of information is essentially based off of this scenario. So you can really think of it as there being as there sort of being like a building here. And the idea is that there is, in fact, a ladder which is sort of leaning on the particular building. And of course, the ladder is not just a line; it's a three-dimensional object. But what we want to do is we want to sort of extrapolate a couple of things. And the first thing is that the foot of the ladder is 8 feet from the base of the building. So if this were sort of classified as the building wall, then the ladder, the distance between the building and the ladder is in fact going to be 8 feet. So we can say that we have x here. If we were to sort of take this particular side as x, or the distance between the ladder and the wall as x, then we can say that this distance x is in fact going to be 17 feet. And it's helpful to actually go off to the side and actually note down the things that we attain as we go. So really, what they've given us thus far is that x is actually equal to 17 feet. And it says that it's sliding away, the base is actually sliding away from the building at 3 feet per second. So you can almost think of it as the ladder, it's actually moving this way. And of course, as the base of the ladder moves rightwards, the top of the ladder is actually going to go down. And what the first part of the question asks is, how fast is the top of the ladder sliding down the wall of the building? So first and foremost, let's just sort of digest what it's told us. It says that the foot of the ladder is 8 feet from the base of the building. We know that. And it's saying that the foot, which is this particular portion here, it's sliding away from the building at 3 feet per second. That is, in fact, a rate of change. So if we could say that that x, that the base, or x with respect to time, the change over of x with respect to time, is in fact going to be 3 feet per second. So this is a rate of change. Wherever you have a measurement and wherever you have two measurements, and one of those measurements is a distance or a length, and the other is a unit of time, we can sort of understand that we have a rate. So dx over dt is in fact a rate in this particular condition. And it's saying that while the length is 17 feet, the rate of change at which the base of the ladder moves away from the wall in the opposite direction is in fact 3 feet per second. And what it asks us here is, how fast is the top of the ladder sliding down the wall of the building? So it's really telling us, um, if we were to assume that this side is y, it's really asking how fast is y falling down the side of the wall as x, essentially as the base of the ladder, or x, gets bigger off towards the right. So if we were to think of it as x gets bigger towards the right, what is the decrease in x? At what rate is that decrease occurring? So it's really asking us for dy over dt, which could be said as the rate of change of y with respect to time. A big question mark here. So in order to do this here, we actually want to relate some of the components that we're given with the component that we want. And a good way to do that is sort of think about some formulas, think about the condition that you're looking at, and try to see if you remember any formulas which can sort of equate what we want to what's given, or what's given to what we want. So in this case here, if we were to sort of recall the Pythagorean theorem, we know that the Pythagorean theorem is two sides of a triangle squared is equal to the other side. And in this case here, it says, we actually forgot to mention this, that it's a 17-foot ladder. So this distance here is actually going to be 17 feet. So if we were to sort of label this distance from here to here as perhaps being z, we could say that z is in fact 17 feet. And again, we're just sort of drawing a diagram and labeling everything, seeing what we have, seeing what we don't have. And we're trying to see if what we don't have is what the question is asking. And in this case, it is. It's asking for the rate of change of y with respect to time. How fast is y changing? So it says here that it's asking us how fast the ladder is moving away from the wall. So it's asking us dy over dt, and we're given x, we're given the rate of change of x, and we're given z as well, which is of course our hypotenuse in this case. So somehow to relate all these components, we can use the Pythagorean theorem, which says that z squared actually equals x squared plus y squared. So this actually relates what we want with what we're given. And it does so in a way, and you may be curious because you're saying that, well, we want dy over dt, we don't want y squared. And the idea is that when we actually try to find out and apply this formula to an instantaneous scenario, we're actually going to end up taking the derivative of both sides of this equation and every single component implicitly. And after doing so, we'll be left with, dy over dt, and I'll show you that shortly. The idea here is when we take the derivative of both sides of this equation, we'll eventually get to taking the derivative of y squared, which is a function within a function. So this warrants using the chain rule. So when we actually use the chain rule here, we'll do the derivative of the outside multiplied by the derivative of the inside, which is y, which is just dy over dt. So this would essentially be your derivative. And if you have this in your original equation, then what you can do is you can actually end up solving for dy over dt on the condition that all the other variables have concrete values. So the idea here is that all the other variables here, z and x squared, or not really x, but x and dx over dt, all of those must have concrete values. And then once they do, we can actually solve for y squared. And what I really mean by that is that if you think of something like this, 4x plus 3 is equal to what? What is x is equal to 0? What is x? You can solve for x in this case because everything else is sort of given a value, right? But if you had, suppose, 4x plus y is equal to 0, you can't really solve for x and get a concrete number. So that's essentially the same idea that we're applying here. So if we actually take the derivative of both sides here, if we were to do d over dt, of course, these are all z squared, and all these other elements here, these are all functions of time. So if we were to take the derivative of both sides, of course, d over dt, we would actually end up, so if we were to take the derivative of both sides here on the left-hand side, it wouldn't be what you think. It wouldn't be 2z multiplied by dz over dt, because z is actually a constant. Z is 17. So since z is 17, you're actually looking at the derivative of 17 squared, which actually goes to 0, because the derivative of a constant is in fact 0. So so this would be 0 on this side here. And if we were to look at what we have here, we'll take the derivative of x squared, which is just 2x. And since this is an application of the chain rule, we're actually taking the derivative of the inside function, which is x, and that's just going to be dx over dt. And we're going to essentially add that to the derivative of y squared, which is 2y, multiplied by, again, the derivative of the inside of y, which is, of course, dy over dt. And again, let's just try to simplify this further so that we don't need to do too much work. If we were to divide both sides by 2, imagine us doing something like this, then our 2's would sort of cancel out here, but and it would go. We would still have 0 on the left-hand side, but those 2's would eventually cancel out. So we'd really be left with something like this. And the idea here is to understand that we could eventually plug in x, which we have, which is, so x is actually not 17 feet. X in fact would be, x would be 8 feet. So sort of a mess up there. X would be 8 feet. And we could plug in x, we could plug in dx over dt, of course, we know that's 3. And then, of course, we would eventually have to plug in something for y and then solve for dy over dt. But the real problem is that we don't actually have y as a concrete value. So before we actually proceed here, can we in fact solve for y in some shape, way, or form? And it turns out there is a way if again you relate your what you already know. You know that this question to some extent wants to apply the Pythagorean theorem, and y is in fact in the Pythagorean theorem. So the idea is if we use the Pythagorean theorem, which in this case is z squared equals x squared plus y squared. If in fact we can somehow take z squared and plug in something for z squared, plug in something for x squared, plug in something for both of these values, then we can solve for y squared. So z squared, we know that z is equal to 17, so this would be 17 squared. And x squared is, in fact, we know that x is equal to 8, so that would be 8 squared. And we'll have plus y squared here off to the side. And if we were to square 17, if we were to do this here, we'd eventually get y squared equal to 17 squared minus 8 squared. And the idea is thus to isolate y into being a single variable. So we would get 17 squared minus 8 squared. And we would actually get y to be 15. So now we've actually used the Pythagorean theorem to actually solve for y, which is actually what you'd expect with the Pythagorean theorem. Given 2 values of a triangle, you can find the other side. So now this doesn't seem to be too difficult, because we can simply have, we have x here, we know that x is 8, and we know that dx over dt is 3, and we also know that that y is in fact 15 multiplied by dy over dt. And the idea, let's see here. So continuing with actually solving it, we would get 24 plus 15 dy over dt. And in attempts to isolate dy over dt, we can subtract 24 from both sides, and then of course divide by 15, and we would essentially be left with dy over dt actually equating to negative 24 over 15. And negative 24, negative 24 is just 8 times 3, negative 8 times 3. And 15 is actually 5 times 3. So dy over dt, if we were to essentially come off to the side here and say that dy over dt is essentially going to be negative 8 over 5. Now, sort of moving on to the next part of this question here, we are asked for, we're essentially asked for how fast. So we've solved the fact, we solved the question, how fast is the top of the ladder sliding down the wall of the building, which would be -8 over 5 feet per second. But we are also now asked for something else. And we are told, part B essentially says, how fast is the area formed by the ladder changing at this instant? So this poses another question. Of course, when the ladder actually falls, the overall area within the triangle will actually decrease along with it. And we know that the area is of a ladder in particular is 1/2 times base times height. Now, in this particular problem here, we've chosen to label the base as being x, so we're actually going to have x here, and we've chosen to label the height as being y. So y, which of course we have a solid value for, which is 15. So if we were to take the derivative of both sides of this formula, we would essentially end up having the derivative of dA over dt. So if we were to take the derivative on this side, and then of course the derivative on this side here, we would pull out the constant, and the constant will be multiplied by d over dt of x times y, which is actually a application of the product rule, right? Because these are two functions. They're both functions of time, x and y. And so this would warrant, in some sense, the product rule here. So going off to the side to actually do the derivative of x times y, that would eventually, using the product rule, we would do the derivative of, x, multiply that by y, and then of course add that to the derivative of y, and actually multiply that by x. And the derivative of x, we said, was, well, the derivative of x would really just be 1, because if we were to use the power rule, then the exponent would come out to the front and we decrement the exponent. We would actually get 1x to the 0th power, which is just 1. But of course, we know that this is a function of time, so that we would actually have dx over dt afterwards. And then, of course, we'd have y, because we're multiplying it by y. And the same thing here, we would have dy over dt multiplied by x. And of course, when we plug this back in here, we actually get that dA over dt is actually equal to 1/2 multiplied by dx over dt multiplied by y, all added to dy over dt multiplied by x. And we'd eventually distribute the 1/2 here. So dA over dt again would essentially equal 1/2 dx over dt multiplied by y plus another 1/2 multiplied by dy over dt multiplied by x. And if we were to plug in essentially what we know, we would essentially have 1/2 multiplied by dx over dt, which we are familiar with is 3 feet per second. And if we have y, which we know is actually 15, we can have that here as well, plus 1/2, and then we have dy over dt, which is, I think we said it was -8 over 5, and multiply that by x, and this would essentially be, multiply that by x, and we know that x as being a constant is 8, so we would have 8 here, all the way out here. And of course this would eventually come out to being your area with respect to time, if you were to sort of do the math there, plug that into a calculator perhaps. Now the last problem in this question tells us to find the rate at which the angle between the ladder and the ground is changing at this instant. So let me go ahead and section off a portion of the board here where we are actually going to solve this problem. So the idea here is that as the ladder decreases, you can imagine an angle here which will also decrease, because as this moves downwards, the overall angle will also decrease. It'll fall on itself, so to speak. And it's asking us to find the rate at which the angle between the ladder and the ground is changing. It's asking for the rate of that particular change of theta. So really what this is asking is it's asking the derivative of theta, the change of theta with respect to time, is essentially what is being was being inquired here. So again, let's think of another sort of a equation which can somehow relate perhaps theta with, can we get theta equated to something in some form and then solve for theta perhaps? A good idea here would essentially be to use our trigonometric functions, for instance, sine, cosine, and tangent, but the idea is which one. So the idea is, let's suppose we chose sine theta. Sine theta, we know on the basis of SOHCAHTOA, we know that sine theta is actually equal to the opposite over the adjacent, or the hypotenuse. So the opposite in this case would be y over, we said this portion was z here. So sine would be a y over z. Now, you could have also used cosine and you could have also used tangent, but the idea is in the difficulty of actually finding the derivative, because once we actually equate theta with to something, we're actually going to end up solving for theta. Or actually we're going to be solving for the derivative of theta with respect to time. And once we do this, in the process of doing so, we're actually going to have to take the derivative of both sides of this equation. And in doing, it's not going to be that difficult, because y is a variable and z is a constant. So you can actually think of y over z as being 1 over z multiplied by y, which is nothing but 1 over 17 multiplied by y, and then you pull out 1 over 17 because it's a constant, and then you multiply that by y, the derivative of y, which is dy over dt, and we know dy over dt because we solved for it here, so it's not that difficult. But what if you were to use, and the same thing could be said for the adjacent over the hypotenuse. You have the adjacent over here, which is y, and you have the hypotenuse, which is z, and one is a constant, one is a variable. Do the same process to find the derivative. But the issue here is if we were to use tangent, we would essentially end up having the opposite over the adjacent, which is y over x. And what you want to remember is that y and x, these are essentially variables, and they're variables on account of they're essentially expressing rates of change. So really, when you take the derivative of let's say adjacent over hypotenuse, like in cosine, or the opposite over the hypotenuse in sine, you can actually use the power rule and just get away with having the derivative. But if you were to do the same with, if you were essentially to do the same with opposite over adjacent as observed with the tangent, this would essentially backfire, because we would actually have to use the quotient rule, given that x and y are both variables. They're changing. Why I say they're variables, what do I mean by saying that y and 8 are variables? Well, because as the angle changes, as the ladder moves downwards, y is no longer going to be 15 and x is no longer going to be 8. The distance from the building to the ladder is going to change as the ladder essentially moves away from the wall, and the distance from the top of the ladder and the ground is also going to decrease. So 15 and 8, these are instantaneous. These are in a particular moment. These are not constants. So we can't take the derivative amongst each other, treating y and x as constants. We want to actually treat z as constant, because despite the rate of change, despite the ladder moving downwards at whatever given rate, z is a constant, the length won't change. So it's best if we use sine or cosine. And in this case, let's just go ahead and use sine. So we agreed that we were going to use sine theta as being y over z. And the idea here is taking the derivative of both sides. We're going to eventually be left with d theta over dt. So if we were to take the derivative of this side, we would essentially have the cosine of theta multiplied by d theta over dt, because of course theta itself is a function of time. And y over z, we know that this can be expressed as, again, 1 over z multiplied by y. And of course 1 over z is a constant, so we can just multiply this by 1 over z. And then the derivative of y is just dy over dz or dt. And of course, we said that we wanted to solve for d theta over dt, or the change in angle with respect to time. But we have some unknowns. Cosine theta is unknown, and so is dy over dt. However, this isn't true. We actually have dy over dt. dy over dt is negative 8 over 5. So we have 1 over 2 multiplied by negative 8 over 5, or not 1 over 2, but 1 over z. And, you know, on the topic of z, we actually know what z is as well. So why don't we go ahead and plug in everything that we do know except d theta over dt to eventually solve for theta over d theta over dt. We know that cosine theta is, in fact, going back to our SOHCAHTOA, we know that cosine theta is actually going to be the adjacent over the hypotenuse, and the adjacent is here, or actually, sorry, the adjacent is here over the hypotenuse, which is here. So cosine theta is actually going to be 8 over 17. Multiplied by d theta over dt. And of course, 1 over z is akin to saying 1 over 17, since z is a constant. So we can actually use that in our derivative. And dy over dt is essentially, as we said before, negative 8 over 5. And if we wanted to solve for d theta over dt, we could multiply both sides by 17 over 8, in which case, if we were to do that, if we were to multiply by 17 over 8, then these 17s would cancel out, these 8s would cancel out, and d theta would be essentially equal to, if we were to look at this here, these 17s would cancel out, these 8s would cancel out. We'd essentially be left with negative 1 over 5, and that's essentially going to be d theta over dt.